On June 19, 1973, astronauts aboard Skylab were measuring the solar ultraviolet spectrum when the instruments recorded something the models had not predicted. The data showed solar radiation at intensities that should not have existed. They did not know that morning that they were measuring the first direct evidence of a process that had already begun, one that will not stop, and one that we can see happening right now, 5 decades later from your backyard. The sun is a sphere of plasma held together by its own gravity, fusing hydrogen into helium at a rate of 600 million metric tons per second, a process that began 6 billion years ago, according to radiometric dating of the Allende meteorite from 1969. This process has no mechanism to stop. It will continue until the hydrogen in the core is exhausted. The question is not if the sun will change. The question is when, and what happens when it does. We do not observe this fusion directly. We measure it through neutrinos, ghostly particles that pass through the entire Earth as though it were not there, 17 billion of them per square centimeter per second, a flux first detected by Raymond Davis Jr. at the Homestake Mine in South Dakota in 1968. The rate at which these neutrinos arrive tells us the fusion rate in the sun's core. The rate has not changed, but the pressure required to maintain that rate has changed and continues to change measurably, in real time. The sun has burned through approximately half of its initial hydrogen supply. This is not theoretical. The current mass of the solar core is approximately 0.34 solar masses, measured through heliosismic observations, vibrations in the sun's surface that reveal the interior structure. When the Michelson Doppler imager aboard SOHO began continuous observation in 1995, we could track these oscillations in detail. And the data showed the core was already denser than earlier models predicted. The core's density has increased because the fusion process itself changes the composition. Hydrogen is converted into helium, and helium is denser than hydrogen. The core becomes helium-rich, while the outer regions remain hydrogen-rich. This creates a density gradient. The pressure at the core's center is now approximately 250 billion times Earth's atmospheric pressure. That number is not stable. It increases as the core becomes denser. Here is the problem that Skylab discovered. As the core becomes denser, the pressure required to maintain the same fusion rate decreases. The core can fuse hydrogen at the same rate, even though the pressure is lower. This triggers a feedback mechanism. Lower pressure means lower density in the surrounding layers. The convection becomes less efficient. Heat accumulates in the core. The core temperature rises. I'll come back to what rising core temperature means, because it changes the entire timeline. The sun is not middle-aged. It is not stable. The sun has already begun its transition to the next phase of its life. The Parker Solar Probe, launched by NASA in 2018, has measured the solar wind velocity and temperature directly. The data shows the wind accelerating faster than models predicted, because the core is already hotter than earlier models assumed. The process is already underway. The sun's luminosity, the total energy radiated per second, is currently 3,828 times 10 to the 26th watts. That is 386 billion megawatts every single second. For comparison, all human electricity production in 2023 was approximately 28 trillion kilowatt-hours annually. The Sun produces that total in approximately 2.5 seconds. But the luminosity is not constant. As the core heats, the luminosity increases. The Sun grows brighter. This is called the faint young sun paradox. It was not paradoxical. It was inevitable. The Sun's brightness has increased by approximately 10% over the past 4.6 billion years. This is not a prediction. This is a measurement derived from the mass-luminosity relationship, a fundamental law that relates a star's mass to its energy output. As the core mass increases through helium accumulation, the fusion rate increases. As the core temperature rises, the fusion rate increases further. The Sun was 30% dimmer when life first emerged on Earth. We're halfway through, and the next measurement is why I made this video. The Sun's core temperature is now approximately 15 million Kelvin. Current models predict that when the core reaches approximately 100 million Kelvin, a new process will begin: helium fusion. The core will ignite, and that temperature is not billions of years away. The core is heating at a rate of approximately 3,000 Kelvin per billion years, according to stellar evolution models refined by Schroeder and Canaan-Smith in 2008. The timeline is narrowing. When helium fusion begins, it will not be gradual. The helium core is degenerate. The electrons are packed so densely that they obey quantum mechanical pressure rather than thermal pressure. The temperature increase will not cause expansion. The core will remain compressed. The fusion rate will accelerate catastrophically. This is called the helium flash. It will occur in approximately 4 billion years, according to current models. Hold that number. We'll need it later. The helium flash will release as much energy in a few seconds as the Sun normally produces in 10 million years. But the observer will see almost nothing. The energy will be absorbed by the surrounding layers. The photosphere will not brighten noticeably. Instead, the core will expand. The pressure will decrease. The fusion rate will slow. The Sun will reach a new equilibrium as a red giant, fusing helium in the core and hydrogen in a shell around it. Mercury will not survive. The inner planet orbits at a distance of 57.9 million kilometers from the Sun's current center. A red giant sun will expand to approximately 250 million kilometers, more than 4 times Mercury's current orbital distance. Mercury will be consumed. Venus at 108.2 million kilometers will likely be consumed as well. Earth orbits at 149.6 million kilometers. The red giant sun's edge will extend to approximately 1.15 astronomical units, possibly engulfing Earth, possibly sparing it by a narrow margin. The uncertainty in current models is whether Earth survives or is incinerated. This is what the 600 million tons per second means. Every second, the Sun is converting hydrogen into helium. Every second, the core becomes denser, hotter, more pressurized. Every second, the lifetime remaining decreases. In approximately 4 billion years, this process reaches its inevitable conclusion. The helium ignites. The Sun expands. The inner solar system is remade. Earth may survive in a distant, burnt orbit, or it may be consumed entirely. Either way, the biosphere ends. The oceans boil. The atmosphere is stripped away. This is not a catastrophe. This is physics. But the red giant phase is not the end. After the helium is exhausted, in approximately 700 million more years, the core will contract again. The surface will cool. The sun will shed its outer layers, creating a planetary nebula. The core will become a white dwarf, approximately the size of Earth, with a density so extreme that a teaspoon would weigh as much as an elephant. This white dwarf will slowly cool over trillions of years, eventually becoming a black dwarf, a stellar corpse invisible and undetectable. 5 billion years is not a countdown. It is a measurement. We can observe this process happening in real time through the Parker Solar Probe, through SOHO, through helioseismic data. The sun is not going to suddenly change. The process was already underway when humans first looked up at the night sky. The process will continue after we are gone. The data from Skylab in 1973 was not a warning. It was a confirmation that the sun's life, and by extension, the only habitability our solar system will ever know, is not infinite. It is finite. It is measurable. And it is already in progress. The reason we track solar activity today, the reason the Parker Solar Probe measures the solar wind, the reason SOHO monitors the sun continuously, is not because the sun might change in some distant future. It is because the sun's life is not stable. It is not an equilibrium. It is a process. We are living in a moment of solar history where the sun is measurably different than it was a billion years ago, and measurably different than it will be a billion years from now. This is not pessimism. This is the view from the data. The mathematics of stellar evolution are fixed. A star of the sun's mass, 989 times 10 to the 30 kilograms, will spend approximately 10 billion years on the main sequence, the stable phase where hydrogen fusion dominates the core. We are 6 billion years into that process. The remaining 4 billion years are not speculation. They are the solution to the stellar structure equations, tested against thousands of observed stars at different ages. The sun's future is written in mathematics that applies everywhere, always. The process requires no external trigger. No collision will accelerate it. No cosmic event will change the outcome. The sun's death is encoded in the fundamental constants, the strength of the nuclear force, the fine structure constant, the mass of the proton. Change any of these by even 1%, and stars would not form at all, or would burn in vastly different ways. But these constants are fixed. They have been fixed since the Big Bang. The sun's death is not a possibility. It is a consequence of the constants that govern all physics. The sun has been dying for 6 billion years. It will continue to die, measurably and inevitably, for another 4 billion years. The process is not accelerating. It is not hostile. It is physics, the unavoidable consequence of gravity and thermodynamics operating on matter at stellar scale. And it is already underway. None of it is aware. None of it is trying to hurt us. The data simply shows what will happen because it cannot be otherwise. If a star's life cycle, from formation through death, can be predicted from its mass alone, what else about the future is already written into the physics? What other processes are occurring right now, invisible in their scale, that will reshape everything we can see? Leave your answer below.